Dear students, in this video, I want to introduce the concept of subspaces of a vector space. Okay, what do you think of subspace? Okay, do you know the concept of subset? Subset means what? Okay, a small set within a big set. Okay, similarly, what is subgroup? Subgroup means a small group by itself within a bigger group, right? Similarly, subring. Okay, similar to that concept. Okay, we now have the subspace of a vector space. So similarly, what you have earlier, similar to that, we now have subspace. Okay, subspace means first you should have a vector space. Okay, so v plus comma dot is a vector space. As usual, we will have a vector space or a field F. Okay, and you know what vector space is. Okay, the 10 properties like v comma plus is abelian group, and you have a external operation star from f cross v to v satisfying some 4-5 conditions like that. Okay, so such vector space we have here. And what is w? W is a non-empty subset of v. Okay, if as we discussed, okay, subset means set within a set, subgroup means group within a group. So similarly, if W is a vector space over F, that means what? W is also a vector space within the vector space V, because already V is a vector space and W is its a subset. So then if W itself is a vector space, then we say that this is a subspace of this vector space V, right? As simple as that. But here we take the same field F. Whatever field you consider for V, vector space V, the same field you consider for W. And moreover, see the first point. Okay, note points. Okay, the internal operation plus, you know, plus is called internal operation and star is called external operation. These are same as that of on V. So the plus and star operations on W are exactly same as the plus and star on V, right? And the field F is also same both for V and W. That is the second point. And if W over F is a subspace of the vector space V over F, then W comma plus is a subgroup of the group V comma plus. Okay, already I discussed here. So what do you mean by vector space? Already V comma plus is an abelian group because it is a vector space. And what is W? W is also a vector space. That means what? W comma plus is also a vector space. Therefore, W comma plus is an abelian group. But what is W? W is already subset of V. Therefore, W comma plus is a subgroup of the group V comma plus. Okay. And the zero vector. See, if you have a subgroup, okay, of a group, you know that the identity element for the subgroup and the group are same, right? E is same. But what is the identity with respect to plus? 0. That is zero vector. So the zero vector is same, okay, for any subspace and the vector space. So whatever zero vector you have, that is whatever identity you have in V comma plus, the same identity exists in every subspace, not only W. You take any subspace, there you have the zero vector. Now next, the inverse, same. Suppose you have a alpha in W, okay, so W in you have alpha in W, but the same alpha is also exist in V because W is a subset of V, and W comma plus is a group, okay, so you have inverse of alpha, but V comma plus is also a group, okay, you have inverse of alpha in V, but the inverse of alpha in W and inverse of alpha in V both are same, they are not different. Suppose beta is inverse of alpha, that is alpha plus beta is equal to, what do you mean by inverse? 0 bar, identity. Okay, if you add them, you will get 0 bar. Of course, beta plus alpha is also 0 bar. Then the same beta works as inverse in W and V as well. Okay, you will not have two different inverses for same vector alpha. That is what I am saying in 5th point. Okay, these are already there in group theory also. Okay, right? Do you remember when we talk about subgroups or subrings, there are two trivial subgroups. What are they? Okay, the singleton identity, okay, and the group itself. Similarly, when you talk about subspaces, there are two trivial subspaces. What are they? So here, okay, what are they? So the identity, singleton identity. What is the singleton identity? That is 0 bar, okay, and V itself are subspaces of V, okay, and these two subspaces are called trivial subspace. That means if you take any vector space V, okay, there are two trivial subspaces. What are they? Singleton 0 bar, that is identity itself as a set, and V itself, okay, are two subspaces of the vector space V. Hope you understand. Okay, these are called trivial subspaces. What do you mean by non-trivial subspaces? Right, any subspace that is different from these two subspaces, that is singleton 0 bar and V, are called non-trivial subspaces. Okay, we will see. Next, and this is the thing, we already discussed it, okay, in the fourth point. Because 0 vector is same for both V and W, you take any vector any subspace W, you will have 0 vector is common for all subspaces. Suppose you have another subspace W2, suppose this is W1, this is W2, definitely 0 bar is there common for both W1 and W2. Okay, so any subspace of V contains the 0 vector. So 0 vector, that is identity with respect to plus, is common for all subspaces, right? Now we will see some examples of subspaces, right? Yes. Now see these examples. You already know this, these examples very well. Okay, what are those? The first one, let us consider the vector space V. Okay, that is the entire three-dimensional space R cube. Okay, so that means the space. Okay, three-dimensional space. That is, suppose this is X, this is Y, this is Z. This is the three-dimensional space. And now what is our W? W is, okay, two-dimensional space. That is, for example, you take X, Y, Z space, that is as V, and now what I am considering, so here the third dimension is 0, that means this plane, okay, this part of the plane, this part of the space is actually a plane, that is, you can assume it as XY plane, okay. This is geometrical meaning, but of course, if you make the third coordinate 0, okay, everywhere, you consider all those points, okay. For example, you have all these points 1, 2, 3, or minus 1, minus 2, minus 3. All these points are there in V. But what kind of points I am considering in W? I don't consider 1, 2, 3, but I consider 1, 2, 0. I don't consider minus 1, minus 2, minus 3 in W, but I consider only minus 1, minus 2, 0. Hope you understand. So the third coordinate is always 0. That means Z coordinate is 0. You can assume like that. Therefore, it corresponds to XY plane. Okay. Then it is a subspace of V. You please pause the video and you can check. That is, W is a subspace means W itself is a vector space. Means what? W comma plus is an abelian group. You can check. Okay. And star defined from, okay, F is what? Real numbers. Real numbers to W, okay, to W. That means what? You take any real number A, okay, you take any vector in W, x1, x2, 0. Then what is the star between them? This is nothing but AX1, AX2. What is A into 0? Is 0. So again belongs to W, no? So therefore, okay, A star alpha, this is alpha, right? Element in W is equal to alpha. Of course, is not alpha, but it belongs to W, right? So external operation is there and it satisfies all the 4 or 5 conditions with respect to this star. You can check it, okay? And thus W becomes a vector space by itself, but it is a subset of V. Therefore, it is a subspace of the three-dimensional space V. Okay. Similarly, we also see the you are also familiar with this vector space V, that is set of all 2 by 2 matrices over a field F. Okay, this is a vector space. You can check it. Okay, V comma plus is an abelian group, and the what is star? Star is nothing but, okay, the scalar multiplication. That means if you have some scalar P, okay, multiplied with the matrix, that is vector is here matrix. So ABCD. So what is the result? PA, PB, PC, PD. Again a 2 by 2 matrix. That means again belongs to V. So this is a vector space. Now what I am considering in W is all diagonal matrices only. Okay, you can check this is also a vector space. That means again W comma plus is an abelian group, and with the respect to same star, okay, W also satisfies the remaining conditions of the vector space, and it is a subset of V because I am not considering all 2 by 2 matrices here, only I am considering diagonal matrices. Therefore, they are part of V, so it is a subspace of V. And the third, see the third one. So we have already seen this example V, set of all polynomials of degree 3, okay, degree less than or equal to 3. So that means you know what you have, okay, all constant polynomials, first degree polynomials, second degree polynomials, and up to third degree polynomials. Okay, it is a vector space with respect to addition of polynomials and scalar multiplication. Okay, now what is W? W is set of all polynomials of degree less than or equal to 2. Here I don't have all these things, only I consider, okay, polynomials up to degree 2. Okay, A belongs to F. What is F? F can be any field. It can be real numbers, it can be complex numbers, anything. Okay, so then with respect to same plus, that is polynomial addition and scalar multiplication, okay, W is also a vector space and hence a subspace of V. Okay, so far I have given you 3 examples of subspaces. Now we will also see the subsets which are not subspaces. For example, you see the 4th example. So again I consider 3-dimensional space R3. Okay, it is a vector space, and I consider W is equal to x1, x2, 1. Do you remember the earlier example? I have taken x1, x2, 0, but here I have taken x1, x2, 1. Okay, the third coordinate is 1, but it is not a vector space because, okay, if W to be a vector space, it should contain identity vector, right? 0 vector. Okay, but what is the 0 vector? 0, 0, 0. But W does not contain this 0, 0, 0 because for an element to become to be in W, okay, the third coordinate should be 1. But if third coordinate is 1, it is not a 0 vector. That is, identity element is not there. Therefore, simply we can say that it is not a vector space. So, W is not a subspace. Hope you understand, right? We will see one more example for a subset but not a subspace, right? Let us see. Now see this example 5. Okay, so in this example I again consider the vector space of 2 by 2 matrices over the real numbers R. Okay, now W, what I have taken W is set of all 2 by 2 matrices with some special condition. What is that condition? AD minus BC is equal to 0. What does this condition mean? It means they are singular matrices. You know what is AD minus BC for a 2 by 2 matrix? It is determinant, right? Det A is 0. When det A is equal to 0, such matrices are called singular matrices. So I consider only set of all singular matrices in V as a subset. Now I want to show that, or I want to verify that whether it is a subspace of V or not, right? See, okay, I want to claim that it is not a subspace. Why it is not a subspace? Do you have 0 vector here? Yes, because 0 vector, what is the determinant of 0 vector? AD minus BC? 0. Yes, it is also belongs to this, but not, this is not the reason why W is not a vector space. I will give you. Okay, so I have considered alpha. What is the determinant of this? AD minus BC? 0. What is the determinant of beta? This is also 0. But if I add 2 vectors alpha and beta, what is this? Okay, but what is the determinant? Not equal to 0. Therefore, this alpha plus beta does not belong to W. Hence, W is not a subspace. Okay, so I have given you 3 examples of subspace, 2 examples of not a subspace. Now, what is your exercise? Your exercise for this class is to find 2 subspaces, 2 examples of subspace and 2 examples of subsets of a vector space but not a subspace. Right? Kindly try to do that, then only you understand. Okay, thank you.